So, why would a black hole, an object famous for swallowing light, be colder than the space around it and still be forced to glow? A typical black hole left by a dead star is colder than the cosmic microwave background, the leftover heat from the Big Bang. That sounds impossible. A black hole is defined by an event horizon, a boundary where the required escape speed would exceed the speed of light, so outward signals fail. Temperature usually tracks microscopic disorder, like atoms jiggling in a hot metal bar. A black hole seems to be just gravity and geometry, yet physics assigns it a temperature. A black hole's temperature is really about information, not atoms. Entropy is the physics term for how many microscopic states can hide behind the same macroscopic description, like countless molecular arrangements all reading as the same room temperature. In thermodynamics, temperature tells you how entropy changes when energy is added, so anything with a well-defined entropy can, in principle, have a temperature. Bekenstein argued that a black hole should have entropy, and Hawking's later calculation fixed the rule. The entropy is proportional to the event horizon area, not the volume inside. That area law is the twist, double the radius, and the horizon's area, and the entropy jump by a factor of 4. So the horizon acts like the storage location for what's hidden. If that boundary carries entropy, thermodynamics insists the black hole has a temperature, and the glow question returns. But where could any radiation come from if an event horizon is one way? The quantum vacuum is not truly empty. Quantum field theory describes space as filled with fields, and those fields fluctuate even at zero temperature. Near the horizon, the intense curvature of spacetime can separate parts of a fluctuation so that one excitation falls inward while another escapes outward. The escape in excitation is Hawking radiation, and the energy it carries away must come from the black hole's mass. So evaporation is literally mass turning into radiation. The surprising part is that nothing climbs out from inside. The radiation is created just outside the horizon by the combination of quantum fluctuations and gravity. We have not directly measured Hawking radiation from real black holes because the signal should be far weaker than surrounding starlight. But the underlying ingredients, quantum fields and general relativity, Einstein's theory of gravity, are both experimentally well tested. Bigger black holes are colder black holes, and that is why many of them are colder than space today. The horizon's surface gravity, the effective gravitational acceleration right at the edge, sets the typical energy of Hawking photons, so weaker surface gravity means a colder spectrum. For a more massive black hole, the horizon sits farther out, and the surface gravity at that larger radius is smaller, so the temperature drops. A solar mass black hole comes out at tens of nanokelvin, while the cosmic microwave background is 2.7 Kelvin, so the net flow of energy goes inward. The black hole absorbs more microwave light than it emits. But shrink the mass down to something like a small asteroid a few hundred meters wide, and the horizon becomes microscopic. And the temperature jumps into the trillion-degree range, and the evaporation time can fall to billions of years. Astronomers look for the final gamma-ray flashes from such objects to test whether small primordial black holes ever formed, which keeps the glow tied to observations. If Hawking radiation is almost perfectly thermal, what happens to the information in what fell in? Information here means the exact physical state, like the microscopic pattern on a hard drive or the quantum state of an electron, not just a story in English. In Hawking's original calculation, each emitted particle looks random, so if you throw an encyclopedia into a black hole and wait for complete evaporation, it seems you get back only featureless heat. Quantum mechanics resists that outcome. Unitarity is the rule that the full quantum state evolves without losing information, even if recovering it is practically impossible. The clash is the black hole information paradox, and it suggests Hawking radiation must carry hidden correlations across many particles, even though any one particle looks thermal. A lot of recent progress, especially in theories where gravity can be translated into a quantum theory on a boundary, an idea called holography, supports that information leakage picture, but it remains a frontier because we cannot run the experiment on real black holes. The glow isn't an escape from the event horizon. It's what horizons do when quantum fields meet thermodynamics. The horizon hides information, so it has entropy, and thermodynamics ties entropy to temperature. Quantum fluctuations just outside the horizon then show up as Hawking radiation, and the escaping energy reduces the black hole's mass. That answers the opening puzzle. Massive black holes have low surface gravity, so their Hawking temperature is tiny, often below the 2.7 Kelvin cosmic microwave background, yet they still emit. When the universe cools below that temperature, evaporation dominates, and the black hole converts mass to radiation. Even an accelerating rocket has a horizon and, in theory, would detect a faint heat bath called the Unruh effect. If this was interesting, hit the subscribe for more and turn that notification bell on.